We continue looking at the SN2 process. So we said we have a backside attack of OH minus, that is a nucleophile, and then the substrate, the 2-bromobutane that had S configuration at the end of the reaction becomes R configuration. So we said that from the stereochemical point of view, we can say that there was an inversion of the configuration. If you start with the S, you get the R. If you start with the R, you will get the S, right? So that will be the stereochemical outcome of the overall reaction. And then now we need to look also what happens when we change the nature of the nucleophile. So how about if instead of using OH minus, how about if I use, let's say, CN minus? CN minus. Is that going to be a better nucleophile or worse? How can we judge if it is a better nucleophile or a worse nucleophile? Well, so a better nucleophile will give me a faster reaction, right? I will get a conversion into product faster. So some other alternatives, I can use CN minus, or I can use SH minus, or I can use water, etc. There are many different nucleophiles that I can use. The other thing that I can change is the solvent. And you could see in the other, in the previous installment, I show you how by running the reaction in different solvents, you can get a different distribution of products. So the nature of the solvent can be extremely important. And then lastly, we have the leaving group. So what happens with the nature of the leaving group? So the leaving group in this particular case was Br minus. So I had to break a carbon-bromine bond. When you look at the location of a bromine on the periodic table, so you can guess that the carbon-bromine bond, yes, is a polar covalent bond, but it's not extremely strong bond. So the breakage of that bond will take place rather easily. But how about if I go, instead of a bromine, if I put a chlorine there? Or worse, how about if I put a fluorine? Well, because fluorine is so much more electronegative, and also the atomic radius of fluorine is so much smaller, so that bond is going to be more difficult to break, right? And that is going to slow down the reaction. So we will see later, one by one, we will examine the nature of the nucleophile, the nature of the solvent, the nature of the leaving group. Before, let's have a look at the next slide of McMurray. And so there you can see that McMurray is using the electrostatic potential map to show you the course of the reaction. So here we have the nucleophile is red hot. Remember that red means high electron density. High electron density. High electron density. And then we have the substrate. You have the carbon atom that is attached to the leaving group, the bromine in this case. So the bromine is looking more orangish, right? Because of the delta minus that you have on the bromine. And in the meantime, because the carbon atom is electron depleted, so that's why you have a delta plus, and that's why it's more bluish, right? And so the color code, blue implies delta plus, while reddish or orangish indicates delta minus. So you have the backside attack of the nucleophile on the alkyl halide. Half the way of the reaction, what happens? This is interesting. Half the way of the reaction, the three substituents that you have on on the alkyl halide, if I go back to our previous example here, we have CH3H and CH2CH3. The three substituents will be in a trigonal planar arrangement. See the three of them? They are in a trigonal planar arrangement there. And as far as the electron density, you will have the formation of the nucleophile carbon bond is half the way. So that's why the nucleophile is still kind of reddish. And then the leaving group has not broken apart yet. So that's why it's still rather reddish. And then at the end, once you have formed the final product, then now you will have the carbon atom will become again with a delta plus once the nucleophile is attached. And then the leaving group, when it departed, it will be completely red, right? Okay, so that is that slide. So let's talk a little bit about the energy diagram that will be associated with such a reaction. So the energy diagram should look a little like this, right? I will have G against progress of the reaction, and you will have the reactants will have a certain energy. Then you will increase the energy, you will go through a transition state, and then it will go down to the formation of the final product. So notice that we have just a transition state. There are no intermediates. There are no intermediates in this reaction. So I cannot isolate any species that is in between the reactants and the products. No intermediates. So here, as we are talking about transition state, there is some interesting idea. I can change the rate of the reaction by altering the energy of the starting material. This is the energy of the starting material here. Or I can change the rate of the reaction by changing the energy of the transition state, right? So if I increase the energy of my starting material, what is going to happen? Now you can see that the delta G1 double dagger, it was this big. But if I increase the energy of my starting material here, right? So then now my delta G2 double dagger will be smaller. A smaller energy of activation means that the reaction will go faster. It will be easier to overcome the energy of the transition state. So that will be one trick to get the reaction going faster. I can intentionally do something that will destabilize my starting material, and if everything else stays the same, so the overall result will be that the reaction will go faster. The other trick that I can do, it will be by altering the energy of the transition state itself. Let's say that this is my original transition state. If I manage somehow to lower the energy of my transition state to this point, so then now the overall rate of the reaction will be faster. And so there you have two different ways to accelerate the rate of the reaction, by increasing the energy of the starting material or by decreasing the energy of the transition state. Let me take advantage to say a little something else here as far as the relative reactivity of different alkyl halides. So here you can see that methyl halides are the most reactive. Why? Well, because if you have just a methyl halide, you have only hydrogen atoms here, and the approach of the nucleophile will be much easier, right? Primaries will be a little slower, Secondaries will be even slower, and the tertiaries, they are virtually unreactive. Think about this. If I have 3 methyl groups attached to that carbon, the approach of the nucleophile, here I have my leaving group. So even if I have a good leaving group, right, the approach of the nucleophile is going to be fairly difficult. So that's why the reaction will be fairly slow. And reaction with alkenyl systems, carbon-carbon double bonds, or with aromatic systems is zero. There is no reaction at all. Okay, I'll stop here and we continue later.